This video begins our discussion on exponential functions. First, we need to review the laws of exponents. Laws of exponents were discussed in intermediate algebra. We'll review them quickly here. If any of these you forget or need more practice, now's a good time to stop, go back and review laws of exponents by using Khan Academy or an alike website. When we multiply two of the same bases together with various exponents, we can add the exponents together. For example, 2 to the third power times 2 to the fifth power is equal to 2 to the eighth power. Also, if you have a base raised to an exponent, and then that is raised to an even higher exponent, then you can multiply those two exponents together. For example, if you have 2 to the third power raised to the fifth power, it's equal to 2 to the 15th power. If you have two bases that are multiplied together to make a product, they have to be multiplied, not added. And if they're multiplied inside, then the exponent can be distributed into both factors. For example, if I have 2x to the third power, that's equal to 2 to the third power, x to the third power. Be very careful. A lot of students will say we have x plus 2 to the third power and think that the 3 can be distributed in, and it becomes x to the third plus 2 to the third. That is not true. That is a FOIL problem 3 times wide. Be very careful. If there is an addition sign in there, then the exponent does not get distributed inside. It can only be distributed inside if the terms are being only multiplied to each other. If you have a base raised to a negative exponent, we always write negative exponents as positives by moving it to the other side of the fraction line. So if a to the negative s, which is considered the numerator since there's no denominator, we could write it in the denominator with a positive exponent. For example, if I have 2 to the negative third power, we could write that as 1 over 2 to the positive third power. And lastly, a to the 0 power is 1. Any number to the 0 power is 1. So we're going to use some of those basic rules to talk about exponential functions a little bit deeper. Exponential form has the form of f of x equals 2 to the x power. Note where the variable is here. It's in the exponent. We're not used to seeing x's as an exponent. 3 to the x plus 1. X is an exponent. G of x equals 10 to the x. J equals 1/2 x minus 1. All of the x's are in the exponent position. Over here, the x's are the base. So that's not exponential form. This is not exponential form because no matter what x is, even though it's in the exponential position, no matter what it is, you'll never turn 1 into any other number. If x is 2, h is still 1. If x is 10, h is still 1. This is actually a constant function. X does not make any changes. Same thing with this position here, because negative 1 to the exponent is never going to be anything besides negative 1. And lastly, this is not exponential because you have both an x in the exponent and in the base position. To be considered exponential, there can only be an x in the exponential position. The base cannot be 1, and the base cannot be an x. So let's graph an exponential function. First, let's find some points on my graph. If I want to graph 4 to the x power, Well, 4 to the negative 2 power is 1 over 4 squared, which is 1/16. So we'll have a point at negative 2, comma, 1/16. If negative 1 is the exponent, we have 4 to the negative 1, which is 1 over 4 to the positive 1, which is 1/4. So we have a point at negative 1, 1/4. Zero, if 0 is the exponent, 4 to the 0 is 1. So we have a point at 0, 1. I think I have these in the wrong spots. Sorry, negative 2, 1/16 would be above. Negative 1, 1/4 would be above. Those are not correct. Okay. 0, 1. If 1 is x, we have 4 to the first power, which is 4. So 1/4 would be a point. And if 2 is x, we have 4 squared, which is 16. So 2/16 would be a point, which is way up there. So my graph would look like this. Now, what would happen if I were to change the base to a different number? Let's take a look at what would happen in a graphical form. Okay, so in the first graph, I will go ahead and do the 4 to the x power. So you can see how that matches the graph that we already graphed up here. Let me zoom in just a little bit so we can see a little more in detail what's happening around the origin. Okay, so that's 4 to the x power. Now what if I change this? I'll also graph 2 to the x power. So I'm going to make the base a smaller number. So if I zoom back out, so the first one, that's 4 to the x, and then this one is 2 to the x. So what that graph is doing is it's still hitting this same point right here, but it's becoming wider. But then it crosses over and it has a little bit more of a rounded edge down here. Okay, so they look very, very similar. They have this one point in common because that it makes sense they would have that point in common because anything to the 0 power will always be 1. So even if the base is 2, you're still going to have 0, 1 as a point. So no matter what the base is, they will always cross through this point. The higher the base, the steeper this becomes, and the flatter, the more L-shaped it becomes, and flatter down at the x-axis it becomes. So characteristics of this graph, regardless of the base, the domain is going to be all real numbers. However, the range is only from 0 to infinity. You can see that there is a horizontal asymptote right down here where this graph never crosses. The 0.01 is included on all graphs, no matter what the base is. The function is increasing continually over the graph. There is never an x-intercept. There is a horizontal asymptote, which I just indicated, and it's at y equals 0. And then the function is 1-to-1 because it does indeed pass the horizontal line test. which means it has an inverse. Okay? Only one-to-one functions have inverses. So let's look at the second page. Let's actually graph this function. It has a fraction as its base. Okay? So let's see what happens to this graph. So let's plug in -2 for the exponent. So this becomes 1/4 to the -2 power, which is 1 to the -2 over 4 to the -2. Well, those are going to flip positions because we don't like negative exponents. So this actually becomes, when you flip this upside down, this actually becomes 4 squared over 1 squared, which is 16. So we'll have a point at -2, 16. -1, when I flip this upside down, this becomes 4 to the +1. So we'll have a point at -1, 4. Anything to the 0 power is 1. So we have a point at 0, 1. Anything to the first power is itself. So we have a point at 1, 1/4. One squared over 4 squared is 1/16. So we have a point at 2, 1/16. So it looks very similar to the graph from the last page. However, it does seem to be pointing the other direction. The similarities that it has is the point 0, 1. It has the point 0, 1. But this seems to be a decreasing function instead of an increasing function. Remember, this was the graph of 1/4 to the x power. And these were the graphs of 2 or 4 to the x power. So the difference is here, they were still exponential functions. However, the bases were numbers greater than 1 over here, but this base was a number between 0 and 1. Notice we don't talk about negatives, because negatives are simply just transformations of the original graph. So this, being a fraction, is a number between 0 and 1. So if I were to look at other variations, you probably can guess what's going to happen if I try to put in a different fraction like 1/2. But let's verify. So the first graph, let's do 1/4 to the x power. Sorry, 1/4 to the x power. And then let's do 1/2 to the x. I did it again. To the x power. There we go. I don't think I got that one right up here. To the x power. There we go. Okay. So the first graph, this is 1/4 to the x power, and that should match what we have over here. The second graph is going to be 1/2 to the x power. So you can see it still passes through this point, but it is a little wider and then becomes a little more rounded at the base, just like we suspected. So some of the characteristics, same as before, except for the function now is decreasing. It's starting high and it's decreasing over time as x gets bigger. So what would the graph of 2 to the x look like then? We already kind of discussed that on the first page. Just to give you a brief graph, we know it's going to have this point. We know it's going to be increasing. So just to do a sketch, we know it would look like that. Any base to the x power will look like this as long as the base is greater than 1. If the base is between 0 and 1, we know it will have that same point, but we know it will be decreasing. So the graphs are almost identical, except for the increasing versus decreasing portion. So in conclusion, the graph of f of x to the equals a to the x power, if it's greater than 1, the graph is increasing. The greater the value of a, the steeper the graph becomes. However, the same function, if the base is between 0 and 1, in other words, it's a fraction, then the graph is decreasing. The smaller the value of a, in other words, the smaller it gets to 0, the steeper the graph becomes. So now we can take those exponentials and we can actually begin to do transformations on them. Let's review transformations. Remember, a vertical translation or transformation is by adding or subtracting a number on the outside of the function. Adding a number on the outside moves it up. Subtracting a number moves it down. A horizontal translation means you're adding or subtracting a number, but this time it's inside the function where the x is. In this case, the x is up in the exponent. So if you add a number inside the function, that actually moves it left. And subtracting a number moves it right. And finally, there's reflections. A negative on the outside of the function is an x-axis reflection. A negative on the inside of the function is a y-axis reflection. If you don't remember some of these transformations, I would encourage you to go back to Chapter 3 and review some of those videos about transformations. In order to graph this particular function, let's first look at the original graph of 4 to the x, and then we'll apply the transformation over here. Well, we know what 4 to the x power looks like. We did that on the first page of this video. 4 to the x we know is going to have this point. Also, let's do another easy point. When x is 1, 4 to the first power is 1. So we know the graph is going to look like this, and it's going to have that horizontal asymptote at y equals 0. But now we're going to apply this transformation. This 3 is being added on the outside of the function, which is going to move the transformation. It's going to move this graph up 3 units. So it's going to move the graph. It's also going to move the asymptote. So the asymptote that used to lie on the x-axis is now going to be located 3 units up. So this point that used to be at 0, 1 is now going to be located at 0, 4. So when we sketch the graph, we get this. So this is the graph of 4 to the x, but this is the graph of 4 to the x plus 3. Let's try it again. Here we're going to do 4 to the x minus 2. So this is the original function, which is 4 to the x power. Now we're going to take this graph and we're going to subtract 2 inside the function, which means we're going to move it right 2 units. So we're going to take this graph and move everything right 2 units. So the horizontal asymptote is not going to move. Since it's just shifting to the right, it's not really giving the illusion that it's moving. But this intersection point, which used to be at 0, 1, is now going to be located at 2, 1. So my graph will look like that. Last page. Now we're going to define the number e. By definition, the number e is equivalent to the limit as n becomes greater and greater, as n moves towards infinity. As this n, this denominator, gets bigger and bigger and bigger and bigger. 1 plus 1 over that number raised to a power of that number gets closer and closer and closer to e. So, for example, let's say n, let's start small, was 1, right? 1 plus 1 over 1 raised to the 1 power is 2. Well, let's now do 2. 1 plus 1/2 squared, so that's 1.5 squared, and I'm going to get my calculator out to help me. So this becomes 1 plus 1/2 squared. That becomes 2.25. And as we get bigger and bigger, let's try 10. This becomes 1 plus 1 over 10 to the 10 power, and that becomes 2.59. And let's go even further. Let's try 10,000. .718. E is whatever number that this 2, 2.2, 2.5, 2.7 eventually is going to get closer and closer and closer to some number. And that number is going to be E. By definition, E, which is usually on most people's calculators, E is equivalent to 2.71828182818 repeating. So you can see we were getting really close to that by taking an n of 10,000. But if that n goes towards infinity, that e number will eventually approach e, which is 2.718281828, and so on. So by definition, e is 2.71828, and then that is repeating. E can also be defined as 1 plus 1 over factorial, 1 over 2 factorial, 1 over 3 factorial, and you could sum all those together. That's another way to find E. This E we can use to solve exponential equations. If we use the law of exponents, and if we know the base to some product, or excuse me, some exponent is equal to the same base to a different type of an exponent, then we know that those exponents must be equal. For example, if I have 2 to the 3rd power, and I say it's equal to 2 to the x power, for example, in order for these two sides to be equal, since they both have the same bases, I know that these two things have to be the same number. Therefore, x must be 3. So to solve for these particular equations, I'm going to try to get the bases to be the same. That's going to be my whole goal. This has a base of 2. That's as small as it can get. I'd like to rewrite 32 with a base of 2. Well, by definition, 2, you might just have to play around with this, but 2 to the 5th power is 32. So I could rewrite 32 as 2 to the 5th power. And the reason I like to do that is so I can have matching bases. Once I have matching bases, I know that their exponents must be equal. So I could state that 3x minus 1 equals 5 and simply just solve for x. Add 1 to both sides and divide by 3. For number 2, we're going to do the same thing. Over here I have e, which is a number. It is not a variable. Remember, e is a number and it's 2.7. So e is not a variable. So we have a base raised to an exponent, and then I can multiply these two things together. I could put this on top. I could make this e to the, there's parentheses there. I don't know why they're not showing up. I can put this on top, and when I have a power raised to a power, we multiply those two things together. So this becomes e to the negative 4x over e to the 3x. Now I can simplify these because when you have a base divided by another base, you can subtract exponents. So negative 4x minus 3x is negative 7x. So now I can set these two exponents equal to each other, and I can solve. So 2x minus 1 equals negative 7x. So if I subtract 2x, I get negative 9x. And when I divide by negative 9, I get 1/9. Number 3, 5 to the x plus 3, that's already in the simplest exponential form. I'd like to write this right side as 5 to an exponent. Remember, this is the same thing as 5 to the positive 1. So if I wrote this 5 to the positive 1 up top, it becomes 5 to the negative 1 power. Now by setting my exponents equal to each other, I find x is equal to negative 4. Over here I have e to the x squared equals e to the 3x minus 2. I already have this in simplest form. I can simply just equal their two exponents to each other. So I have x squared equals 3x minus 2. So I'm going to have a quadratic. In order to solve quadratics, you can either factor or use the quadratic formula. I'm going to factor x minus 1 and x minus 2, which means x equals 1 and 2. Over here, this is already in simplest form. 2 is the most pure form of a base. 4, I want to try to break down into something smaller like a 2. Well, 4, by definition, is simply just 2 squared. So I can turn 4 into 2 squared raised to the x plus 1 power. And so then I'll have similar bases. Let's simplify the right side first. A power raised to a power means we multiply those two powers together. So that means that 2 has to get distributed. So this becomes 2 to the 2x plus 2 power. Then I can simplify by setting their exponents equal to each other. And subtracting 2x, I get x equals 2. And last one, 3 to the x squared minus 7 equals 3 to the what power makes 27? 3 to the third power makes 27. So we're going to multiply those two powers together. So this becomes 3 to the x squared minus 7 equals 3 to the 6x. And then we set their exponents equal to each other. So we have x squared minus 7 equals 6x. Let's make this a quadratic. And then we factor. So this becomes x minus 7 and x plus 1. So that means x equals 7 and negative 1.